This video is all about recursion. Recursion, although it does not have too much of theory, it's very difficult to crack in the interview scenario. You may be stuck thinking how to break this problem recursively into its sub-problems. This video will not make you a master of recursion. Obviously, for that you need lots and lots of practice. Here I will try to help the beginners who are starting with recursion problems and they find it difficult how to tackle recursion problems, especially during interviews. So let's begin. So first of all, what are the main components of a recursive problem? So of course there is one base case, and this is probably the easiest thing. People are able to find out the base case. Then we have another thing which is most important, that is recursive relationship or recursion relationship. So this involves breaking this main problem that you are getting. Main problem may be of the form like fn, or it may have more variables. So I am taking just one variable for simplicity. You can have m, n, o. For example, let's say you are solving a grid problem, 2D grid problem. So here you will have some m rows, n columns. So here it will become fmn. So let's ignore these things for now, and let's assume that you have a problem, a function fn, where n is a variable, and you have to break it into some smaller subproblem. That is, fn can be expressed in terms of fn minus k and some more things. Some more things may involve further fn minus k1, fn minus k2, and so on. So let's ignore this. So you have to express this in terms of some smaller number, the same variable but smaller values. And if you keep going down and down, you will ultimately reach the base case. So these two are the main components of this. So in order to solve for fn, you have to think how to solve fn using fn minus 1. So let's assume that fn minus 1 is there. So somebody says that I give you fn minus 1. Now use this fn minus 1, and again I am writing minus 1 for simplicity. It can be some other value also, but smaller than this. So I have given you fn minus 1 and it works. How can you use it to solve fn? So this is the main challenge. So this idea is coming from proof by induction. You must have taken some mathematics class, and one of the ways of proving theorems was proof by induction, and that's a very natural way of proving things. So let's briefly recap that, then we will come back to this. So in proof by induction, what we do, we are given one problem statement, like let's say we have to prove that sum of first n natural numbers. Let me write some shortcut, k, where k belong to n. Let's say n denotes natural number, and here let's write ki from I equal to 1 to some value n. So we are summing up first n natural numbers, and it's equal to n multiplied by n plus 1 by 2. So we have to prove this. So first we will take a base case. So base case will be similar to what we take in recursion, the base case. So we take n equal to 1. So what will be this right hand side? It will be 1 multiplied by 1 plus 1, 2 divided by 2. So it's 1. And clearly it's correct, because first one natural number, sum of first one natural number is just 1. So it's correct. Base case is correct. Then we have to make one assumption, that let's say this is true for n equal to k. Then sum of first k natural numbers will be k multiplied by k plus 1 by 2. So this we assume. So let's say it's true for n equal to k. Then if we can prove that if it's true for n equal to k, then it will also be true for n equal to k plus 1. then our job will be done. And why it will be done? Because we know that it's true for 1. And another thing, so it's true for 1, that is first condition. And second, we want to prove that f of k implies f of k plus 1. So if it's true for fk, then it will be true for fk plus 1 also. If we can prove this, then our job will be done. Because fk implies fk plus 1, that means 1 is already true. So if it's true for 1, then using this, it should be true for 2. Because fk, if fk is true, then fk plus 1 is also true. So 1 implies 2. Similarly, by the same logic, when k is 2, if it's true for 2, then it will be true for 3. And if it's true for 3, it will be true for 4, and so on. And same way, it will be true for n minus 1. And if it's true for n minus 1, it will be true for n, using this second thing. So this is the main thing. So fk implies fk plus 1. Similarly, this we are trying to solve here, that if we are given n minus 1, this implies fn. So this is some idea of mathematical induction. Let's come back to our original problem. Or here let's complete this also. So let's say it's true for k, then what will be the sum? Sum will be, sum of k plus 1 will be, first k plus 1 will be plus k plus 1, the last number. So it will be k plus 1 plus 2 times k plus 1 divided by 2. So we can take k plus 1 common, k plus 2 divided by 2. So you see it's true for k plus 1, n equal to k plus 1. So k plus 1 is n, k plus 2 is n plus 1. So if it's true for k, then it's also true for k plus 1. So combining both, we can prove it. So hence proved. So this was just a brief recap of proof by mathematical induction. Now let's say we are given the same problem and we have to solve it recursively. That what is the sum of, now let's come back to coding. Find sum of first n natural numbers. And again, if you are forgetting about natural numbers start from 1, 2, 3, 4 and so on. The numbers which we use for counting. So it will not include 0. So 0 is included in whole numbers. And 0 is not there in natural numbers. So here we don't need to figure out the formula, but can we express it recursively. So we can define one function. Let's say we are returning int sum and the variable is n, this input. It's also one int. So we know that if think of the base case. So if n equal to 1, this is the smallest natural number, what will be the sum? Sum will be just 1. So we are trying to find this. So if n is 1, clearly sum is 1. So we will write accordingly here. If n equal to 1, return 1. So we have completed the base case and the easier part. Now let's write the second part, that is sub problem step or recursion step. So now we will think how we can, if we are given sum till n minus 1, let's say till here, how we can use it to solve the complete sum. So this is what fn, or in this case sum n, and what is this part? This part is nothing but fn minus 1. So fn is nothing but fn minus 1 plus n. So otherwise we return n plus sum n minus 1, and the function is complete. So this was an easy problem, and it was just to give you an idea how to figure out n in terms of smaller values. So try to break it. So we have written explicitly here. You can even write many other problems, break it into its sub problems, and then try to find which things we can combine to find a smaller recursive function and then add something. So also it's important that whenever you write a recursive function, you add extensive logs for your learning purpose and try to figure out the order in which these functions are called and with what values. For example, let's say we have to calculate sum 5. So this will be 1 plus 2 plus 3 plus 4 plus 5. That is 9 plus 3, 12 plus 3, 15. So this sum 5 will come here. N is not 1. So it will write n plus. So we called sum 5 and it called 5 plus sum 4. And this sum 4 called 4 plus sum 3. And this called 3 plus sum 2. So if you try to figure out the recursion stack, the complete stack or the recursion tree, then slowly and gradually you will start building the recursive intuition. So always try to understand the way in which things are called, at least till you are a beginner. Again, this is not a base case, so it will call 2 plus sum 1. Now when this is called, it will return 1. This is the base case, so it will return 1. So this sum is 3, so it will return 3 here. Now this complete thing is 6, so it will return 6 here. 6 plus 4, 10. So 10 is returned by this, and this 10 is added to 5, and this function finally returns 15. So this was a small example to give you an idea of how you can think about the recursion tree. So you should always try to understand it completely. So now that we have seen one recursive problem, a simple recursive problem, let's write what are the different components of a recursive function. So we have a recursive function foo, and it has n. So it will have one base case which will return something xyg depending on the base case, and then we will have a sub problem or the recursion which will try to call foo again with some smaller value of n and k. Then we will have some other code. So this is the typical body of a recursive function. Now once you have solved this and understood this, let's try to solve following problems. So let's pause it and try to solve the factorial. So you have to find factorial of n. So how you will do that? And just if you are not familiar with factorial, n factorial is nothing but 1 multiplied by 2 multiplied by 3 all the way up to n. For example, 3 factorial will be 1 multiplied by 2 multiplied by 3, that is 6. 4 factorial will be the same thing multiplied by 4, that is 24, and so on. So use the same approach and come up with the solution for this factorial thing. So hopefully you might have written it correctly. So factorial of n will be, think of the base case. So when n equal to 1, what is the factorial? It's just this thing. So 1. Return 1. Else return. So in this, let's try to break it. We have 1 multiplied by 2 multiplied by 3 all the way up to n minus 1 multiplied by n. this is n factorial or fn. So if you take till this step, then this will be fn minus 1 and this is n. So n multiplied by fn minus 1. Now let's take another problem. So gradually throughout this video we will look at harder and harder problem. So next, try to find the nth Fibonacci number. So let's assume that Fibonacci number starts from 1. We have 1, 1, 2, 3, then we have 5, 8, 13, 21 and so on. So this is equal to the sum of previous two. Similarly, 5 is equal to 3 plus 2, 8 is equal to 3 plus 5, 13 is equal to 5 plus 8. So add the previous two Fibonacci numbers. So how can you solve it? So pause the video and think for a while and then come back. So hopefully you might have guessed. Here we have the function fib n and some return type, let's say int. So think of the base case. So what is the first Fibonacci number? We have 1. And what is the second Fibonacci number? It's again 1. So this is fib 1 and this is fib 2. And from third onwards you will have two Fibonacci numbers available to you. So if n is less than 3, return 1. This is the base case, we have written it. Else what we will do? So this is first Fibonacci number, this is f3, this is f4, this is f5. So you may not find a straightaway relationship like this. So what you will need to do, of course you will think of the base case. Then once you have thought of the base case, also try to think of some larger size examples which are larger than base, but not some general value but some concrete value. Let's say try for 3, try for 4, 5, and we will see some examples of these also. And using these, let's say you solve for 3, 4, 5, try to figure out how is 4 converted to 5. That is there some link that I can find it? So you may have to do lots of rough work, some calculation, and try to visualize what's the relationship between 3, 4, 5 and so on. It's not specific to this Fibonacci problem, it's in general. So here you see that nth Fibonacci number is the sum of previous two, that is fifth Fibonacci number is the sum of f3 and f4. So fib 5 is equal to fib 4 plus fib 3. So in this case, using this you can get an idea that otherwise return fib n minus 1 plus fib n minus 2. Although this recursive approach is not a good approach for this Fibonacci since you will be solving it multiple times. So let's draw the recursion tree. So you are calling for fib n. So it will call fib n minus 1 and fib n minus 2. Now first this will be solved, then this will be solved. So this will be in the stack, call stack, and until this returns, it will not start. So in order to complete this, it will further call fn minus 2, fn minus 3. And this will be solved first, then this will be solved. So this will further call fn minus 3, fn minus 4. And let's say after some time it returns. Then this will again call fn minus 4 and fn minus 5. And when this complete thing returns, this left hand side, this will start expanding. So this will call fn minus 2, 3 and fn minus 4. and this will again call fn minus 4 and so on. So you see that you have already solved fn minus 2 here, and again you are solving it. Similarly, if you have solved fn minus 3, but you are again solving it. Similarly for fn minus 4 and so on. There will be fn minus 4 is solved here also, and here also you are solving, and this will again call fn minus 4. So that's why this recursive approach is not good for Fibonacci, although it's good for understanding the concept. So this is where we cache these values. So first time we solve it for some value of n, we will cache it. So that's where dynamic programming comes into picture. So not all recursive problems will involve dynamic programming, but if we are finding lots of overlaps so that we don't need to solve them multiple times, we can cache those values. So next time when this branch is solved, it will automatically keep fn minus 2. So here when this is solved, it will come to this and it will see that this is already present in the cache. So it will directly return in O of 1. So this is an extension of recursion. If there are too many overlaps, then save those values. So after this base case, if there is such scenario, what we will do, if cache dot contains n, then return cached value. So again, if it's present in the cache, it will return this, otherwise it will continue. So if you add this caching step, also called memoization, then it will work. Otherwise this will be wastage of computation. It will compute the same thing again and again. So you need to be good in recursion in order to solve dynamic programming, because in all the dynamic programming problems, the first thing is that you have to, again there also you will start with some base case, and then you have to figure out how you can break that into smaller problems. For example, this same thing, Fibonacci is one example of this dynamic programming. Then let's say you have some graph, you have this source and you have some destination, and there are few other nodes. So from S, these three nodes are connected. There are a few more connections like this, and let's say there are many more nodes. So you have to find the shortest path from S to T. So what you can think, let's say this is node 1, or let's call it A, B, C. So you know that you have to find shortest path from S to T. And if there is a recursion, there need not be an explicit n all the time. This may be implicit also. Like let's say here you are given a graph which has 100 nodes. So implicitly, not directly, but implicitly you can think that this n is also there. Let's call it n. F S to T, and we have 100 nodes. So you know that in order to find the smallest path from S to T, first step that we have to take is one of these three. These three are the neighbors of S. So either your first step will be here to A, or to B, or to C. Now after the first step, your job is, so it breaks into three things. F A to T, destination remains same. F B to T, F C to T. And also you have taken one step, so maybe this length is L1, L2, L3. So this you have to add in the shortest path. So plus L1, plus L2, plus L3. This is part of this. And you have to pick the minimum of these three. So let's say, so in these cases, now how many nodes you have? You have one less node, and if you come to A, you will not go to B. If there are other paths of reaching to other way to reach from A to B, why would you take that? You would have straight away taken this. Or maybe you take that path also. Maybe this was 1, this is 1, and this is 1. So you can reach B in 3 units, and let's say this path is not there, all the paths will go from B, and let's say L2 is 10, so it will come like this and not go to B. So now you have one less node to care about. You will never go to S again because that will be extra overhead. You were already at S, so why would you take a circle and come back to S and then continue? So implicitly you see that number of nodes is decreasing. Earlier we had 100 nodes, now we have 99. Although this does not help you much in this kind of problem. So N will not be there, but you should think that we are making progress. So from S, these are the only 3 ways. Either you go to A or B or C. And there is a cost associated with each of those selections. These are the path lengths. So you see a recursion is falling here. And now let's for a moment think about the base case. What will be the base case? Base case will be that you are already at that. You have reached there. So base case will be if S equal to T, that is you have reached there at that node by making progress. You have came from some path and now you have reached here. So you call FTT here. So if S equal to T, then return 0. So base case is done. Now from S we can go to A, B or C. So otherwise return F A to T plus L1, or rather we should write min of these 3. F B to T plus L2 and F C to T plus L3. So min of these 3. So this F is expressed in terms of sum of other F's. So this is a recursive relationship. But again, just to highlight the dynamic programming, this solution is perfectly fine and it should work. But again, just like the Fibonacci case, here you can solve the same problem again. Let's say from A also you reach this node X, and from B also there is a path you reach X. While trying all the paths from B, you will take X and maybe this is Y. So while solving for A, while solving this first relationship, you might have already found the shortest path from X to T, Fxt. So no need to solve it again when you come from B to X. From X to T you will have already some value. So again add caching here or memoization. So this is again not just a recursive problem but a dynamic programming problem, because there are high chances of overlap. So now you have some idea of recursion. So now let me give you some more problem. So let's say we have a grid. Now let's come to a grid. We have a grid. It has m rows and n columns. And you start from here. The start is in green. This is start. And you have to reach here. And you have to find number of unique paths. So in interview scenarios, you may not be given a ready-made function. First thing would be to write the function signature. So you will think that I have two variables m and n, and I have to return a count number of unique paths. So the function is f m and n. So this is the function that we will define. Now you will think, what is the base case? So what can be the base case, smallest base case for this? So we have m equal to 1, n equal to 1. We have just one cell. So this is the top left cell, and this is also the bottom left cell, bottom right cell. So green and red are here. So in this case, what will be the number of unique paths? It will be just 1. So So if m equal to 1, then we have one path. Now let's add to it. Let's say we have this 2 cells. Now you have to reach from here to here. Again there is just one path. Now let's expand it further. We have 3 cells. You have to reach from here to here. Again there is just one path, and no matter how many cells you add, it will have just one path. Similar is the case for this vertical scenario. If you have to reach from here to here, there is just one path. So if you try these few examples, try to visualize it with the smaller values of m and n, you will find that if any of them is 1, in this case m is 1, in this case n is 1. So if m is 1 or n is 1, return 1. So base case is done. Now how we can solve it further? So let's take an example. So let's say we have 2 cross 4. So we have 2 cross 4 and we have to start from here and reach here. So from here, let's make progress just like we did in this graph problem. So from S we can go to these 3, and from here we will solve. We will never look back. We will only look in this direction. And here one main thing I forgot to mention. Here you are allowed to travel in 2 directions. Either left or either right, that is from left to right, or down. These 2 arrows denote the directions you are allowed to take so that you don't go back. So now let's make progress. This is the starting point. So where can you go from here? You are allowed to take either this direction or this direction. So when you take this direction, you will reach here. And when you take the down direction, you will reach here. Now you will never go back. There is no turning back. So now you are here and here. So your task is, you cannot go to any cell to the left of this. So I am drawing it like this. Similarly, if you are once here, you cannot go up. You will only remain below it. Similarly, you will only remain to the right of this. So now you have broken this into 2 things. Earlier it was F 2 to 4, 2 and 4, 2 rows, 4 columns. Now you take either this step or this. You have to take both the steps because you have to write all the paths. So once you come here, you are concerned only about this part of the grid. So let me draw in green. This part of the grid in green. And when you come down, you are bothered about this part of the grid in red. So what is this red thing? This is 1 row and 4 columns. 1, 4. And what is this green? This green has 2 rows and 3 columns. So if you find all the unique paths from this point to this, and this point to this, and add them, then we are done. So similarly, again from here you will go either here or here. The same logic will expand, and this will return immediately. This is the base case. If one of them is 1, return 1. So you write F24 equal to F14 plus F23. So if you took this example, you might have arrived at this conclusion. So naturally you would have thought, what if we have some general m and n? What will be the scenario? I am skipping some of the cells here in between, and you are here in this cell and you have to reach here. So again 2 directions are allowed. So one of the possibilities will be to go here, second one to go here. Once you come here, you cannot go left. So you will be concerned with this part only, this in blue. So if this is m cross n, what is this blue part? Blue part is same number of rows. and one less column, so n minus 1, plus when you come here you cannot go up, so you are confined to this part of the grid, and here you have one less row, that is m minus 1, and same number of columns. And you are done. Finally, one of them, if any of them becomes 1, you return 1. Otherwise, you keep decrementing it. So here also we are writing mn in terms of m minus 1, n minus 1. So we are making progress. So I hope this problem gave you some enough intuition about recursion. So you should always think of some base case and not just base case. So after base case, don't directly jump to this generic case, but it would be good to take a few examples like this, and from here examples where you can manually write down all the cases. For example, in 2 cross 4 you can write all the paths. Let's say we have 2 cross 4, so one path is go like this here, then come like this, come here, and then down. 2 paths, then third path, and then fourth path. So this should have 4. So try to work with some cases, some realistic values of inputs, so that you can manually write down all the solutions. Then from there you try to build this generic relationship. So now once you have done this, I would recommend you to solve the flood fill problem. This will give you some good idea about grid based problems using recursion. And then let's look at another example. One of the places where recursion is used a lot is binary trees or n-array trees, but binary trees are the most common and easier to explain. Or let's say we will look at a more specific case, binary search trees, where the search property is valid. That is, all the nodes in left subtree will have value less than this node, and all the nodes in right subtree will have values more than this. So let's say you have a problem based on binary search tree where you have to find range sum of binary search trees. So what is meant by range sum? Here you will be given a range, some value L and R, both inclusive. So you have to iterate through this complete binary search trees, and this node will have different values. Let's say L and R are 3 and 5, both inclusive, and this binary tree is like 10. This part will have 8, 9, 7, 5, 2, 3, and so on. So this means that add the values of all the nodes whose value lie in this range. So you start from root, you check root is more than this larger value, so all the values in the right subtree will be larger, so no point in traversing that. Come to left part, and so on. So let's say you are given this problem, so how you will approach it? So first let's write the function signature. So you are given root and you are given 2 inputs, left and right values, both are inclusive. How you will proceed? So first you will think of the base case. So what can be the base case? Base case would be that root is null. Then in that case you will not do anything. Otherwise you will have one global sum, let's call it sum, initialized to 0. So let's write DFS. And then return sum. So we have not done anything here. We have just delegated everything to this DFS function, and we will make it recursive. So let's define the DFS function. This is where we will use our recursion concept. So clearly if root is null, we will return. So let's add a check. If root equal to null, return. Otherwise we will proceed. So if root dot value is in this range, so you will need two checks. So I am writing it mathematically. So this means belongs to, and this means closed range. This open bracket means open range, that is excluding this. So this will mean take till r minus 1, not r, strictly less than r. Here it means till r, even r is valid. You can have mixed intervals also in the math. One is closed, one is open. In this case, both are closed. So in code you will write like val is less than equal to r and more than equal to l. So if this is the case, then sum plus equal to root dot val. This is a valid scenario where we will add. If root dot val is more than l, more than l means it's also more than r. That's why it came here. This is the case where it's more than l but less than r. So more than l means it's more than r also. So in that case we are here at some node and its value is more than the required range. So all the nodes in right subtree will also have values more than this. So we will only look in left part of this. So we will call DFS root dot left LR. So again here you see that there is no explicit n or m given like in these problems involving grids or single n. Here you have to think that n is there. Let's say this had completely, this left side has nl number of nodes, right has nr number of nodes, and one is root. So you are given n implicitly. This is nl plus nr plus 1. This is n. So this initially had nl plus nr plus 1, and here we have expressing this in terms of nl. So nl plus nr plus 1 is broken into f of nl or f of nr. So this is definitely less than this, or in worst case at least one less than this. So here also n is not explicitly given, but you have to visualize that we are either excluding the right part or left part. So we are reducing the number of nodes, and we are also excluding the root because root value we have explicitly checked. So in this case call this, if it's less than L then it's less than R also. Then in the final case call DFS root dot right LR, and we are done. So here also we are making progress. So now you have some good idea of recursion. Now let's take a harder problem. It's a popular problem that's highly recommended for understanding recursion concepts, and it's called Tower of Hanoi. So here you have three towers. Let's call them X, Y, and Z. And you have a few disks on them like this. And you have to transfer all the disks from X to Y. So this is source, this is destination. And you are allowed to use this third tower also. This will be the helper tower. And there are some rules. That's why it's complicated. So the first rule is that a smaller disk should be above larger disk. So like this is invalid. So here you see a larger disk above a smaller disk. This is wrong. It should be always a larger disk and then a smaller disk. So this is first rule. And the second rule is that you can only move one disk at a time. Otherwise you would have taken everything and placed it here. There was no challenge. So one disk at a time. These are the two conditions. So now let's think of the base case as usual. N equal to 1. So here n is number of disks. So let's name them. So we have this X and it has just one disk, D1, and then we have Y and Z. So let's write the function signature. So we have F, or let's call it Tower of Hanoi. X is the source, first one is the source, second one is the destination, and third one is the extra tower that we are given. And we have N. N is the number of disks. So this is the function signature. Now our job is to break it in smaller values of n. So these can be in different order, but we will make progress once we can express this in smaller values of n. So let's take the base case n equal to 1. Then we can directly move this from here to here. So D1 will come here. So what we did, we wrote D1 from X to Y. This was for n equal to 1. So let's erase it from here. So this is very simple. Now let's take a bigger example, n equal to 2. So we have two disks now, D1, D2. So first we can take one disk at a time. So if we put D2 here, then the idea is that we will take D2 from X to Z. So what will happen? D2 will come here. So let's remove it. Now this is D1. Take D1 from X to Y. So D1 comes here. Next, we have to take this D2 on top of this. D2 from Z to Y. So this D2 will come here. And let's remove it, and we are done. Our goal was to transfer all the disks from here to here, and we have done it. Now let's take a bigger example. Now let's take n equal to 3. D1, D2, D3. So first we will take D3 from X to Y. So D3 is here. Now we will take D2 from X to Z. We cannot put D2 here on Y because larger one will be here. So we have to put it here. So D2 is here. Next, we can take this D3 from this Y to Z. So we are putting this on top of this. We are allowed to make that. We cannot put this here, and we will also not put D2 back here. Otherwise we will go back to previous step. So we will put D3 from Y to Z. Now we have two disks here and one disk here, so we will put this D1 here, so D1 comes here. Now you may notice that it has reduced to this problem where we have two disks instead of three, and we have to shift this two disks from Z to X. So if you can straight away think of the recursive problem, you can stop here, but if you are not able to figure it out yet, let's write the other cases also. So once we have done this, what we will do, we will move this D1 from X to Y, we have already moved. Then we have this problem for n equal to 2. So we will put D3. So this I have not written. D1 we moved from X to Y. That's why it came here. Then we will move D3 from Z to X. So this D3 will come here. Then we will move D2 from Z to Y. So D2 will come here. And finally we will move this D3 from here to here. And now we are done. So last we moved D3 from X to Y. And we are done. We have solved it. We have moved all the three from here to here. Now let's see some pattern here. So if you look at the just n equal to 3 case, you see that we have D3, D2, D3. That is first and third are common. Middle one is different. And if you look at n2 case, first and third are same, middle one is different. Now let's look at the source and destination. X, 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 X. That is these two are same. These two are same here also. Then these two are same. This one is different. This is different. These two are same. And this and this are same. Z and Z, Y and Y. So this is a special case of this. So what we had done in after these three steps, we had moved. This was nothing but we have moved two of the disks from X to Z using Y. So if you remember, after these three steps, two disks had come here, D2 and D3, and D1 was lying here. So this will be nothing but moving two disks. So last parameter we forgot. Moving two disks from X to Z using Y. And this is a separate step which is nothing but moving one disk from X to Y. So it's TOH X to Y using Z and N is 1. And this is again the same thing. You will notice that first and third are same. First and third are same. Middle one is different. Then these two are same. These two are same. And this is same as this. So this is also TOH. Here we are moving from Z to Y using X and again two disks. So now you can write Tower of Hanoi X to Y using Z and number of disks is 3 as the sum of X to Z Y 2 disks plus, not plus exactly, you have to repeat the steps, X to Y using Z 1 and finally Z to Y X 2 and also the base case. What will be the base case? If n equal to 1, then you know the base case. So let's write it generic. This was not a generic n. So TOH X Y Z N TOH it will be X Z y n minus 1 TOH x y z 1 and TOH z y x n minus 1. So this means that first you have 3 towers x y z, you have n number of disks, so move n minus 1 disks, n minus 1, and this is the last one. Move n minus 1 disks from x to z using y. So now these n minus 1 will come here and gone from here. Then you will have just one disk here. So just move this one disk from x to y, which is this step. Move one disk from x to y. And finally, this will be empty. This will have this last one, the largest disk. So you will move this n minus 1 disks from z to y using x. Z to y using x. So this is Tower of Hanoi. And when n is 1, you know the base case. So this was a bit tougher problem. So I hope this video was useful. I tried to give you some intuition so that you are not stuck in these recursive problems and you are making some progress. Of course, you cannot get expertise by just watching at these lessons. You need to practice and practice a lot. Recursion is one of the topics which require lots and lots of practice in order to develop recursive thinking. So you have to solve more and more problems and then develop this kind of thinking. And I would recommend you filtering out problems based on recursion from LeetCode, HackerRank, and Geeks for Geeks, and then start with smaller problems and then go towards medium and harder problems, and ultimately with some practice you will start getting recursive thinking. You will develop this thinking. So all the best.